Okay, let's have a quick look back for this one. This is where we launched a projectile 5 meters in height in this direction at 10 meters per second at an angle of 30 degrees to the horizontal. We saw that in order to calculate the time to reach the ground, we could use our SUVAT here, our constant acceleration formulas, and we also took, just for fun, moving in the downwards direction as being positive. The end result from that was it gave us the value for U being negative and gravity being positive. We were trying to work out the time that takes to hit the ground, so using our SUVAT equations we were able to get the value of time being one of these two values, but time's got to be greater than 0, assuming of course we started the experiment at 0, so therefore we're down to only one of those values. Our next job was then to calculate the range, and in order to calculate the range we don't have any acceleration in the horizontal direction, so we can just use our velocity times time for the displacement in the horizontal direction to calculate the range. That's essentially what I've done here. I've kept the time as like with a couple of dots after it, because what I've done is I've just stored the time into the calculator and I just keep recalling that value when I need it. So 10 cos 30 times 1.642 gives me this value here, and again I've just indicated with a couple of dots at the end of there just so that I know that I've stored that in my calculator and can recall back that accurate value again. Now the last bit, which we had fun and games on, was calculating the speed and the angle just before it lands. So looking at the vector just before it lands, the velocity would be in this direction, and that would be taken at this point here, so it's coming in this direction here. And the idea behind that is I'd like the speed, so the magnitude of it, and I'd also like to work out the horizontal angle. Now if you recall, a brief discussion about that would be if this was the ground here, this would be the angle of theta it's making at it with the ground, and we can see that that angle there will be the same as this angle here, will be the same as this one here, and we know that because they're of alternate angles. So ladies and gents, let's have a quick look how we do that one. Our horizontal speed was constant, so that just stays as is. Our vertical speed, we use v is equal to u plus at, and I've just substituted in the values for there. Again, notice that the u was the negative version, and I've got the g for its acceleration multiplied by the time, giving me the square root of 123. Bit of Pythagoras here, and then square rooting in order to work out my answer, and round it to two significant figures, as I'm working with gravity as two significant figures. Okay, and that's how that one's worked out. And the last bit we need to do is calculate the angle, so a little bit of trig applied to that. I've got my opposite side, which was this bit here. I stored that in my calculator. There it is, and it's over 5 root 3, which was the adjacent side here. Quick bit of trig, again, round it down to two significant figures. Okay, that's how that question is done. Notice that it has that type of style that if you want to calculate the range, you need to calculate the time, and you'll more than likely get that time that's taken to reach the ground. Once you've got that time in there, you can then multiply the horizontal speed, which remains constant, or the horizontal velocity, which remains constant, by the time taken for it to reach the ground. Okay, so now the idea with this one is that we've got a projectile launched with a velocity, and this time round we're given this is our vector, our initial velocity, which is launched with. So it's got a horizontal speed of 2 and it's got a vertical speed of 7. Just a quick refresher, we will recall that for vectors, velocity is equal to, well, initial velocity plus at, and then we make sure we got it in vector notation. Likewise, we can recall that the position vector is equal to its initial position plus, and then this is just your s is equal to ut plus half at squared, written again in vector form. And that, for instance, would calculate if I said I had a position over here, like so. I could draw, obviously that vector was supposed to go to the dot. I could call that as its position vector r, and it allows me to calculate the position of a point on there. Let's see if I can get rid of those so I don't crowd up my diagram. Right, so we had the horizontal position, a horizontal velocity of being 2, the vertical one of being 7. We're supposed to calculate the time for the particle to hit the ground, so we can use our constant acceleration formula. So for part 1, I would start bouncing through this type of idea again. I've taken upwards as being positive, so my displacement, well, it's going to be the time, the hitting the ground, so it's gone in the vertical direction, hasn't traveled any distance. Its initial velocity in the vertical direction, taken upwards as being positive. Better write that in there. Upwards as being positive, so anything moving in the upwards direction is positive. Its final velocity, I don't know what that is when it hits the ground. Its acceleration, this time we're going to go with negative g because gravity is acting downwards and we're talking anything moving upwards is positive, and the time is something that I want. Right, an equation which has everything in it apart from v is s is equal to ut plus a half at squared. Might just be able to finish this before I get kicked out. Substituting those values into there, we've got 7t, displacement was 0, we've got a minus, acceleration was g, so we've got 9.8 divided by 2, so it's 4.9 t squared. The value of time then for that, if I plug that into a calculator and get it to solve it for me, so what have we got? Minus 4.9, so that needs to go in minus 4.9. We've got 7 in there, and we've got 0 for that. We get out the value of time being equal to either 10 over 7, and hopefully it comes out as 0 as well, or 0. So that gives me my 2 times. First time 0 at that point there. Let's try again. 0 at that point there, and at this point here the time is 10 over 7 seconds. Okay, and that's that one done. So time equals 10 over 7 seconds. And let's try and finish that off. Alright, ladies and gents, I'd like you guys to have a go at this part here. That's page 489, 490, exercise 21.2, and please do check with the answers as you go through on page 580. Okay, any other issues that you guys have during the week, then please come find me. Thank you.